revise what we have done. We did relativistic wave equations, okay, and we have shown the problems with the relativistic wave equations, okay, and then finally we have figured out how Dirac equation arises from some group theoretical considerations. Clear? So that's all till now what we have done. Okay, so let's forget everything what we have done. Okay, so let's begin afresh a new topic. Okay, so everything will come then. Whatsoever we have done, you will see. I mean, it will emerge automatically from the formalism what we will be doing. Clear? Okay, so we'll be doing the field theory now. Before doing the field theory, so let's review the classical mechanics quickly. Let's have the particle mechanics. Okay, single particle mechanics, I should say. Not a single particle. Rather point particle, I should say. Clear? So how we describe a particle? Okay, how we write the state of a particle in classical way? So you describe it by the position, yes. Okay, suppose if I have a particle, let's say moving from one point to the another point, clear? So let's say point A to point B, okay? So you specify its trajectory, let's say Q, clear? Okay, so it will depend on some parameter. So here we will be taking the time as a parameter. It is simple non-relativistic mechanics, clear? Not the relativistic. And then you specify the velocity, okay? So this will specify me the state of a classical particle. Okay, so coordinate will specify me simply the coordinate where the particle is, and the velocity will just describe the history of the particle. Okay, so it will allow the it will specify the history. It has gone from, let's say, point A to point B. Clear? So these two are important variables. They are linearly independent in nature. Okay, so this describes your configuration space. And based on this thing, we define a mathematical function, what we call the Lagrangian. Okay, so it's an energy function. Okay, its dimensions are energy. So it's a plain and mathematical function. Okay, so we define it as the function of this position and the velocity. Clear? Okay, and of course sometimes the parameter time, but if we assume there are no sources and sinks, so that means you are having, so there is no friction at all, I should say. Okay, the motion does not damp. Okay, this Lagrangian is dependent on this. Lagrangian is defined this way. Clear? And we define another mathematical function, what we call the action. Okay, so this action we define as the integral over time L dt. Clear? Okay, so I'll write this as L, Q, and Q dot. Okay, so this action is a fundamental quantity from which, okay, so if you know the action of a particle, you can describe you can derive everything. Okay, you can know everything of the particle. Clear? So action gives you the all information, and action you write through the Lagrangian. Clear? Okay, so now let's derive the equation of motion based on this action. So that principle is known as action principle. So you should know these things. Okay, so action principle is that, so action principle states that there exists, okay, since there are infinitely many possibilities, let's say you move from A to B, so there are infinitely many possibilities in going from A to B, is it? So all the possible trajectories are there. Action principle says there exists an extremum, okay, so which gives you, okay, so there exists an extremum. So there are, in other words, there exists an optimal path which the particle follows. Clear? Let's say if you are in 2 points, the optimal path is a straight line. The particle will go through a straight line. That is the shortest possible distance. Clear? So these are this is the crux of the action principle. What it says you are having this del variation in S is equal to 0 if you make the variation of Q, let's say. So let me take, so let's say you are having this trajectory, Okay, so how in principle we do it? Let's say, assume the path you know. Okay, you assume this is an optimal path. Okay, so just put a variation about this very path. So like this thing. Let's say this is a variation. So these are all the variations. Clear? So let's assume this is let's say this is a delta q. It's a small variation. Okay. So if you vary the path, what will happen to the variation? So it will simply change the s. Clear? It will make a variation in s. What will happen then the variation of s? So it should be 0 because I am assuming this path to be the optimal path at the extremum. Clear? So the variation about that very path should yield me the 0. So that is the way we are doing it. Clear? Okay, so let's do it. So if I am changing, let's say this q to some q plus delta q, so the velocities will get changed, is it? So what will happen to this velocity? So it will be q, so variation in this q dot, so that's actually q dot plus d by dt of what? Q delta q. Clear? Okay. So now let's write this using this kind of concept. So what will be the variation in s? So it will be simply dt. So what you need to put, just put a partial derivative of L with respect to the first coordinate, multiply the variation in the coordinate, plus partial L by partial q dot delta q. Okay. So there is one point which we have not mentioned here. So you can fix the endpoints. Clear? So let's fix the endpoints of the path. Okay. Then, okay, we'll be having, this is the boundary condition. Let's say TA. So this is the initial time, and this is the final time. So the variation at endpoints is equal to 0. Clear? Got it? So there can be the another boundary condition. You can fix only one endpoint and allow the another point to be varying. Clear? Got my point? Or you can be having another thing. So you allow the path to change. Okay, you don't make the endpoints fixed. Clear? But you can assume it follows the equations of motion. So these are the kinds of boundary conditions you can apply. So but we'll use this kind of boundary condition. Now let's integrate this term by parts. Okay. So why I need to integrate it by parts? Okay. Delta q's are independent. Okay, but delta q and delta q dot are not independent. Okay. So I want to free it from this dot, so that you are having only one variable, delta q dot. Okay, so let's integrate it by parts. So what you will get? So I'll be having this delta s dt partial L by partial q delta q, okay, plus, so let me, what is the first term? When you integrate by parts, partial L by partial q, okay, so it will be simply delta q evaluated at endpoints, okay, so I should put the endpoints here, integral dE dB, okay, d by dt partial L by partial q dot, okay, clear? Okay, so now this term goes to 0 at endpoints, and so it is a boundary term. Clear? So you are having now by definition this is equal to 0. What it means? It means this term minus this term. So like this thing, partial L by partial q minus d by dt partial L by partial q dot, that has to be equal to 0. So what are these known as? So you are having Euler-Lagrange equations. Okay, so this they describe the equations of motion. Clear? So this is how we do it. Any question? Okay. Okay, so now a simple example you can take. Okay, so if you know the Lagrangian, okay, so you need to figure out the Lagrangian. So that I will tell you later on how to construct the Lagrangian, but for the time being, let me take the Lagrangian to be like this thing. Half of m q dot square, let me write m x dot square minus v of x. So let's take this as a simple Lagrangian. Okay, so this is the kinetic energy of the particle minus the potential energy of the particle. Okay, we'll come later on how to construct this kind of Lagrangian. Okay, so but we'll assume this is a Lagrangian. Okay, we'll assume it, the form will assume. So now you can write equations of motion. So what is the coordinate here? It's x. Clear? So I need to construct a partial by partial x. So that is simply minus, so partial v of x by partial x, because this is the only term which depends on x, so it's minus gradient of v. Clear? And now then I have to construct this partial by partial x dot. So this is the term which depends on x dot, so it will be simply m x dot. So therefore you substitute there, you will be having d by dt of, okay, m x dot minus partial okay, L by partial this thing, so that will be minus gradient of v, that's equal to 0. What you get? M x double dot is equal to minus. So what this is? So this is the Newton's law. Okay? So these are the Newton's equations of motion. Okay. So this Lagrangian is defined in the configuration space. Okay? So now let's construct a quantity and move to a new space, what we call it the free space. Okay? So let's say you are having one space q and q dot specified, and another space it is given by q and p. Okay? So there exists actually a map. So it's simply you need to define a Legendre transformation in going from this configuration to this configuration by defining a map. Okay, so let's say I need to define actually the map, what we call sometimes a Legendre map, partial L by partial q dot. So it is the what we call as a canonical momentum. Okay, it's a canonical quantity conjugate to q. Okay, what is changing? Q dot. Huh? So q remains, q goes to q, but q dot goes where?
Q.
P. Sorry.
P.
So it's P. Clear? So so we define a quantity what we call as a canonical conjugate momentum. Okay? So this is a conjugate quantity to coordinate. Okay? If you know the coordinate of a system, then you should know, then you should calculate what? Its canonical conjugate. So that we call as a generalized momentum, but we'll say it as a momentum. Clear? Okay. So now the point is here, since we are interested in defining what is the energy of the particle, Lagrangian does not specify me the energy. It is an energy function. Clear? So here when I go to from this space to this space, so I will figure out what is the total energy of the system. And if you, what is the function that describes the total energy? So it is the Hamiltonian. Hamiltonian depends on coordinate and the momentum. Clear? Okay. So for that matter, how I define now the Hamiltonian? So I define a quantity Hamiltonian as P q dot minus L. So this is simply the Legendre transformation. Clear? Samajh aa? So have you done Legendre transformation somewhere? Okay. So what is the idea of the Legendre transformation? So if you see, let's say you are having a, what this describes, this P partial L by partial q dot, it's a derivative. And what derivative specifies me? Tangents. Clear? So that means this will specify me what? The tangent. Okay? Roughly, you can speak roughly it is a tangent to the curve defined by L. Clear? So that means you are now moving from some, let's say you are having a curve. Okay? So at every point of the curve, you uniquely specify a tangent. Is it? Is that true? Okay, so once you specify the tangent, now you are actually in the tangent space itself. You are not in with the curve itself, but you have described yourself with the tangents. Clear? So this is the idea of, this map. Clear? Okay, so there is one important point. Let's say I am considering here only one particle. Okay? So since Lagrangian depends on position and the momentum. Clear? position and the velocity. So in general, this generalized momentum, this P should depend on Q and Q dots, is it? Samajh? So this I can define only when this equation is invertible, because P will depend on Q as well as Q dot. You can see Lagrange, since this is a function of what? So this is a function of Q and Q dot. In general, we say this P, this generalized momentum, is dependent on what? Q and Q dots. Okay, let's say if there is a Q square and Q dot square, or Q and Q dot square, so you will get a function of Q and Q dots. Clear? So this should be invertible. What does that mean? I should be able to solve this equation for Q dot and Q in terms of P. You got my point? So look here, I am solving this equation for P in terms of Q and Q dots. Clear? But if I invert it, what does that mean? I need to solve this equation for Q and Q dot in terms of P. Got my point?
Yes.
So that is the invertibility condition here. Okay, so this will appear, okay, when you take the many particles, so it will become a matrix. So you will be having many coordinates, many momentas, so then you can make it as a matrix equation, so that then the determinant of that matrix should be non-zero, so that it is invertible. Clear? So this equation I can define only when this is an invertible map. Clear? Otherwise we will be having a problem with this equation. Samajh aawa? You got my point? Everybody followed it? Because what I am trying to do, I am actually writing this function in terms of momentas, not in terms of Q dots. Clear? Because I require a Q dot here. If it is not invertible, that means I cannot specify Q dot, is it? So this Q dot will not be specified here. Clear? Samajh? Now take an example, this example. So now let's write this edge. So you are having now P. What will be the P? First I need to calculate P. So it's partial L by partial this thing. So it is simply mx dot. So differentiation of this thing. So it is, this is the momentum, m times v. This is a momentum of the particle. So what you are having is, so it is P. What is no? So it is P by m. Clear? Sorry. So let's write first mx dot into x dot minus half of m x dot square plus v of x. So what is that equal to? Half of m x dot square, okay, plus v of x. But what is x dot? It's equal to P by m. So that's the correct formula. So that means it will be P square by m plus v of x. So you have to use this very formula. Huh? You have to invert it. Now you can see if this is not invertible. Let's assume this is not invertible. You cannot write this x dot then in terms of P. Got it? Because this function is defined entirely where? While you are having Q and P, you don't have velocities here. Samajh? So you should make a differentiation between the two quantities. Clear? So in other words, we are having this Hamiltonian H as a function of Q and P. Okay, so we have gone from this function L of Q dot, okay, to this function Q P. Clear? Any question? Huh? So now how to write the equations of motion? Although these are okay, so in phase space, how to write them? Okay, so let's take this h. So I am having, okay, so let's take this function h of qp. So let's write this dh. So can you tell me how I can write it? Yes. Okay, so let's write it. Sorry, so this h is actually equal to p q dot minus l q dot. So now let's write this dh, total derivative of this. So it will be p then d q dot plus dp q dot. Clear? Minus, now what it will be? Partial L by partial q, then dq minus partial L by partial q dot dq dot. Although it is delta q, I will put dq. Huh? Clear? Okay, so now what Now let's use the momentum, partial L by partial Q dot. Clear? So if I use partial L by Q dot here, so then this term and this term goes. Okay? Is it true? Is there any error? No. So now what about this partial L by partial Q? So let's use the equation of motion. You are having d by dt are partial L by partial Q dot minus partial L by partial Q is equal to 0. Clear? So then what this object is? Anybody? 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 So what is this thing? This is P, is it? So it is d by dt of P is equal to partial L by partial Q. So that means this object is P dot. Huh? So it is simply P dot. So therefore, I am having this dH is equal to Q dot dP minus P dot dQ. Clear? Got it? So now I can write therefore, which implies, now let's take the Q dot. So it's equal to partial H by partial P, and you can have the P dot is equal to minus partial H by partial P. So we call these as the Hamilton's equation of motion. Okay. So that means, so in configuration space you are having the Euler-Lagrange equation, which will give you the equations of motion. In phase space, these are actually Hamilton's equations of motion. Clear? So these are not actually the equations of motion in the strict sense. And if can anybody tell me why? What we call it as an equation of motion. Newton's law is an equation of motion. What does that mean, mathematically speaking? So it contains double time derivative of the position coordinate of a given variable, is it? So you are having an acceleration, clear? Yes, so, but what you are having in Hamilton's equations? What you are having? Only single time derivative, okay? So in that sense, it's not an equation of motion, huh? Clear? Okay, you should think over it. Can we call these as an equation of motion in the strict sense? I mean, in the usual sense, in light of the equation, in light of the Newton's laws. So since we are here in the phase space, we call them as equation of motion. They govern the dynamics of the particle. Okay. So this will give the evolution of the coordinate, and this will give what? Evolution of the momentum. Clear? So both the because you are having here two coordinates which will specify me the motion. Okay, that is Q and P. Okay, so now we define another quantity. Okay, so what we call it the Poisson bracket. Poisson bracket. So how we define it? So let's say you are having two variables f1, two functions which are the function of, let's say, pq, okay, and f2 is also the function of pq. We define a Poisson bracket with respect to qp variables, with respect to the canonical conjugate variables q and p. Okay, so how we define it? So you take partial f1 by partial q and partial f2 by partial p. So this is the definition: partial f1 by partial p and partial f2 by partial q. So this is how we define. So it is only for the single coordinate. If you are having many coordinates, then you need to put a sum. Clear? So this is the Poisson bracket. Now let's calculate the Poisson bracket of two canonical conjugate variables. So I should put a p here. So let's say q and p, these are, so let's take p here. Okay, so let's put the Poisson bracket. So it's partial q by partial q, partial p by partial p, minus partial q by partial p, and partial p by partial q. Now partial q by partial p, it is 0. So this object is equal to 0. So this is 1. So you are having Poisson bracket is equal to 1. So this forms the definition of a canonical conjugate variables. Okay. So if the Poisson bracket of the two variables, okay, canonical, so then we call them as a canonical conjugate variables. So here Q and P are canonical to each other, conjugate to each other rather. Clear? And we can write now the equation of motion in terms of this Poisson bracket. Okay, how? Anybody? So let's say if I have to take, let's take some variable f and figure out its total time derivative. Let's say f is an observable. Clear? So let's take its time derivative. Okay? So how I will do it? Can anyone tell me? So let's write f is a function of p, okay, q, p and t. Let's write. Okay? It's an so I don't say it's an explicit time dependence. It can have both explicit as well as an implicit time dependence. Clear? Because this you can take q and t also time dependent. So now let's take the total time derivative of this f. F is an observable quantity. How I will write it? It will be simply first a partial f by partial t. Clear? Then plus, okay, then you, since it's a total derivative. Clear? Samajh aa? So you can, okay, if you are not able to understand it this way, so let me write it. Let's write df. Let's take a total variation of f. Clear? So what it will be? Since there is a variation with respect to time as well, so it will be partial f by partial t multiplied by dt. Then you will be having partial f by partial q dq plus partial f by partial p dp. So is this clear? So this is how we can write the total variation of f if it depends on q, p and t. So you can have this partial f df by dt. So it will be simply partial f by partial t plus partial f by partial q. So it will be dq by dt. So it is simply q dot plus partial f by partial p. What it will be? P dot. Clear? Okay, so what is q dot? So let's rewrite this thing. So it will be partial f by partial q. What is q dot? So it will be partial h by partial p. Yes. So what is p dot? Partial h by partial q. Great. So it's partial h by partial q. Clear? So you are having a minus, and what this yield is mean? So this is equal to simply the Poisson bracket between f and h. Clear? So therefore I am having the time evolution of a variable f or an observable given like this in terms of the Poisson bracket. H is the Hamiltonian of the particle, or the energy of the particle. Clear? So now if there is no explicit time dependence, this partial f by partial t goes, and if the Poisson bracket vanishes, then okay. So if f has no explicit time dependence and Poisson bracket fh it's equal to 0. So what you get? df by dt is equal to 0. So it means f is a conserved quantity. So if there is no explicit time dependence and Poisson bracket is equal to 0, it means this thing. So or I can have the condition for the Poisson, okay, conserved quantity means f and h should be equal to 0. Clear? So if you have a conserved quantity, its total time derivative is 0 or its Poisson bracket is equal to 0. So they imply each other. Okay. So this is all about the particle mechanics. So now let's go to the fields. Let's generalize the coordinate to the concept of the field. Any questions till now? Okay. Okay. So let's take the concept of the field. Okay, now how you define, okay, before going to the field, we have done the electric field, clear? So how we define an electric field? Not mathematically, give me the definition, sir. How we define an electric field? So you are having a field there, is it? A term field is there. But electric is before, then field. What is an electric field? Yes, it is a space. Around a charge where you can feel. So that means how you define a field now?
Hypothetical space.
Yes, it's a region.
Yes.
Okay, then what?
We should have some properties.
Okay, we should have certain properties, clear? Huh? So I can define in a simplest way field as a set of numbers. It is essentially a set of numbers which give you the variation of a given quantity at a given point. Let's say you are having an electric field. You define it as a position x. Clear? What this will represent? It will represent the variation of that quantity, is it? And that variation is simply the variation of the electric field. So those are simply numbers. You can measure them by the numbers. Magnitude of electric field is this much, magnitude of this, okay? So that means essentially you can specify the point in that region by certain numbers. Clear? Samajh rahe ho? You got my point? Huh? So in a simplest way, you can think a field is essentially a set of numbers which represent the variation of a given quantity at that point. Okay? So now let's make it more general. We will not take the mathematical rigorous mathematical definition. We will have a physical intuition. Okay, so let's take a membrane kind of thing, or let's say you are having a net at something discrete. Okay? So let's assume you are having this is the distance between, it is very small distance. So let's call this distance A or some delta. Delta is the separation between these points. So this is having a discrete structure. Clear? Let's assume delta is uniform. So you are having a uniform distance between the points. All the points are equally separated. Or in other words, you are having certain region, now divided by these squares. Clear? Smallest squares. Okay. So now how you, let's say if you are having a quantity specified by at each point by fi. I is an index, a discrete index. Clear? F is a quantity which takes value at a given point. Clear? So that means you will be having a value of f here. Clear? You will be having a value of f here. You will be having a value of f here. Is it? But you will get a discrete values. Clear? Samajh rahe ho? You got my point? Okay. So now what I will do, let me vary this distance. Let's take this distance of separation to be equal to 0. So what I mean by that, let me take this delta tends to, what does it mean? So the discreteness of this very structure changes. So it goes into a continuum limit. You can think these points are on a continuum. Clear? Samajh rahe ho? So the nature of this index is gone. So okay, we started with what? A discrete index, you are having a discrete values at every point. Clear? You got my point? Now what I am saying, let's take this delta tends to 0. What will happen? So this point will come to near. So what happens? So discreteness is gone. So a continuum emerges. Clear? So that means this function will now depend on, instead of this discrete index, it will depend on certain coordinate. Is it? At a given point. Clear? So that means if you need to measure this very function, you measure it at a given point x, where x is a continuum variable now. Instead of a discrete variable, what it is? A continuum. So that means you will be getting this function as a continuous variation over certain point. Clear? Samajh rahe ho? I can say, let's say f is a discrete variable. Now I can say f of x as a continuous variable. So this f of x will define as a field. So it will, since it defines me the value at a given point, is it? So I can say this f of x now represents a field. Okay, define it in certain region. समझ आओ? The same way you are having now. Let's say if you take this region, let's say if this f is an electric field, you can think these points, at each point you are having a charge, is it? So you can get a discrete value. Okay, so for each charge you will get some value, every value. Now let's bring the charges closer. So what you will get? So you will get a continuous charge distribution. Well, how you will represent that? By certain continuous function. Clear? And the field produced by that will be a continuous function over that region. Is it? Got it? So this is actually an idea of a field. In other words, let's put it in a very simple terms. You can think, let's say if I am having a scalar field somewhere, that means in a region you define at each point of that region a scalar quantity. Clear? You can think that as a coordinate, okay, of that kind of field. Samajh aaya? Got it? Instead of, okay, so it will be some kind of a general coordinate representing that region. Samajh aaya? Not the coordinate in the usual sense. Clear? Everybody followed it? What a field means? Huh?
So why we not define it on discrete? Why we need to make it continue?
So yes, a field is a continuous function. So you cannot define the concept of the field, in a discrete way. Clear? So this is this form is actually what we call as a manifold. It is actually a continuum. On a continuum you define, okay, so on a continuum you define certain kind of function. Clear? Okay, so think of the fluid. Fluid is moving. How you describe the fluid, velocity of the fluid? By the velocity field. Huh? Huh? Because look here, you will be having the velocity at different point. It is not same everywhere. Okay, so you will be having one vector somewhere. Okay, so it is actually a continuum of something. So entire you represented by some velocity function. Clear? And that velocity will be the function of the coordinate. Clear? Samajh aaya? Let's say you are having now, so this fi was only defined at this kind of thing. So this f of x will give me what? The value in the neighborhood of this x. Clear? So that means, because x will be now varying continuously. So you will get that continuous variation where? In this f. But here it is not varying. So you are having a discrete value. So value of f at one point, value of f at another point. Okay? Clear? So here you are actually changing a coordinate in a continuous fashion. Clear? And you are getting the value of a function which you are defining in this very region. So that function we call as a field. Okay? Huh? So this is a physical idea of the field. There is the mathematical subtlety is there, but that is too beyond for you. Okay? So, but for this class, it suffices to define field in this way. Clear? So otherwise, I have to define two types of manifolds, a base manifold and target manifold, and put actually the mapping between the two. That will give you the concept of the field. Clear? Okay, now look here. Let's think of the electric field. What kind of field it is? It's a vector field. Okay. So let's take the temperature.
Scalar.
Huh?
Scalar.
Is temperature a field? Huh? Is temperature? You are having scalar potential, is it?
Yes.
So what is that? That's a field. Clear? No? Scalar, you define scalar potential at every point. Okay? So that's a field. Samajh aaya? Okay. So okay, now think of a membrane. you can, okay, so instead of the membrane, okay, forget. Okay, so let's say if you are having the variations on the membrane is a continuous thing, clear? So let's specify the function, some function. Let's specify the variation on the membrane. Okay, so what it will be? So it will be a continuous function. Let's assume phi of x will give me the amplitude at a given point. Okay, so but it will be in the continuous fashion, clear? So you don't define it on a single point, I mean on a point, but you define it in the overall region, clear? So but once you need to take what is the value at a given point, you supply it by the coordinate at that point, clear? So that nature is there. Let's say phi of x represents the potential, clear? Now I am saying what is the phi at some point 1, 2, 3. In 3 dimensions, okay? What is the value of function? So it will give me the value of the field at that point, and it will be simply a number if it's a scalar field. Now if it's a vector field and I am giving you a point here, x value, let's say e of x, and I am giving you x, like 1, 2, 3, clear? So it will give me a vector. So the output will be the vector, clear? But it will be a vector at that point, clear? Okay. So now let's try. So now we are moving from actually some discrete to the continuous systems. Clear? Okay. So we have done the particle mechanics. Okay. Now we will do it for the continuum systems. How to define it? Clear? So. Okay, so here, let's say in the Lagrangian mechanics, so you define Q and Q dot, clear? So since we will be doing in the four dimensional space time, Minkowski space, I am assuming now there is a Minkowski space. Okay, if I am now taking the fields, we will be doing field theory in 4 dimensional space time, Minkowski space time, clear? So I will take position and time on the equal footing. So that means these will specify me the coordinates of a point, x and t, clear? So you should remember it. Okay. So you are having coordinate here. So let's assume for the coordinate I should be having a similar quantity, clear? So what I call that as a field. So let's call this as a field here. So on what quantity it should depend now? Field. So it will be the position at that point. Huh? So x, you specify the value of x. Clear? It is now the 4 space time. X is a 4 vector here. Okay. So you specify the value of x, you will get the value of the field there. So instead of now the single this q, what you are having? A continuum variable. Clear? What we call as a field. Okay. Now for q dot, what I should be having now? So I should be having phi dot as well. Clear? Because I should be having a time derivative object there. But when I say in this very region, I am having space and time on an equal footing. Clear? They are independent of each other because they are the coordinates. So I should, in addition to this phi dot, I should be having a derivative of phi here, a space derivative. Clear? So that means the configuration here, in this case, the state is specified by q and q dot, clear? In a simplified way, I should be having the state here specified, or a given point, or a given field, sorry, a given point in a field, it should be specified by me by these quantities, clear? So much are the state of a particle in a continuous system, it should be specified by a field, its time variation, and it is space variation, clear? Because it depends smoothly on time as well as space, clear? Any question? Okay, so what is the function here which specifies me that quantity? So that is L, Lagrangian, clear? So here is also a quantity what we call the Lagrangian density. We are, instead of density, we often call it as a Lagrangian, but we'll use term Lagrangian density, clear? So much for the timing, we'll use the Lagrangian density. So that means if you are having a the function which will govern dynamics here, so we call it as a Lagrangian, okay, and the function what will be governing this very objective, so what I have here, Lagrangian density. So how I define the action? S is equal to integral L dt. So what it will be here? It will be, so first if I am saying it as a density, I need to construct the Lagrangian first. The definition of the action is same. Clear? Action is same. What I need to construct? Okay, I am giving you the mass density. I want you to first calculate what? Mass. From density you calculate the original quantity. Clear? And then you put there. Clear? So what I will do, I will calculate like this thing. L, so integrate this over volume. Since it's a density, so you integrate it over volume. And then what you are having? S is equal to integral dt. Clear? So this is how we make a transition from discrete to continuous. But there is a one catch. Now look here, you are having a function that depends on the function itself. So L is a function, phi is a function, phi dot is a function. Okay, now look here. L is a function of variables, simple variables. Q and Q dot are the variables. Clear? So now you are having instead of, so phi is a function of coordinate. Clear? So you are having x is a variable here. Phi is a function, but this is a function of the function. So this is a transition. So you are having there only the functions. Now you are having a quantity, what we call it the functionals. So we call these as the functionals. Functional means function of functions. Okay, so let me give the definition of the function in a, then we'll take later on these in detail. So functional means, okay, so if I am giving a function, let's say if I am giving a function of some variable f of x, and you supply the value of x, what you will get? A number. Use, okay, so you are having a function means it is a mapping between, obviously x and y, so it's a mapping between what? A variable and a number. So it maps a variable to a number. Clear? So f of x is a function, okay? So you supply the value of x, what you will get? A number. Now look at the functional. You need to supply the value of a function and you get a number. So let's say you supply the value of phi here, these things, you supply the value of here, what it maps? So then it will be a number. So functional maps actually functions to the numbers. So those numbers can be real or complex. Clear? So this is the basic difference between the function and the functionals. Or more simply, you can think functional is a function of functions. Clear? So much common? Okay. So now I can write. Okay, so look here. So this action is a, okay, so let's write this action. So I can write this action for the continuum system as integral dt. What is L? Integral d3x. Okay, so you can see now. So you are having phi of x. So I will put simply it as partial mu phi of x. Clear? So partial mu means both. So what it is? So it is d4 of x. Now you can see it is a functional. So it is now more clear. So what is an action? Action gives always a number. Okay? So what is the input here? A function. Input is function phi, is it? Okay? So then it evaluates, provides you a number at hand. Clear? So this is the action for the four-dimensional space-time. Clear? So of a field phi. This phi can be any field. It can be a scalar field. It can be a vector field. It can be, okay, so they can be any types of fields. Any question? Any question? So this will be our starting point. d4 of x is what? Okay, so now the point is, there is one important point. So here we specified the region of the motion from, let's say, A to B. Is it? In this case. Now what is the region here? So we take entire space-time. Clear? So it is entire domain. So entire domain where these fields are defined. So these fields can stretch to infinity. You can be having a finite region as well. So it is the entire domain. Clear? समझ आया? Okay, so one more point here. So there is a property of this action. Since we are in the four-dimensional space-time, it should be Lorentz invariant. Clear? So this action should be Lorentz invariant, or it should be actually a Poincare, more generally Poincare invariant. What does that mean? If you are a Poincare group, means Lorentz group plus a translation group. Clear? So this means Lorentz transformation plus translations. Okay? So now look here, d4 of x, it's invariant under Lorentz group. Lorentz transformation. So d4 of, so you are having d4 of x is same as what? d4 x prime. Clear? So this is invariant under Lorentz transformation. Now if you take translation, translation means you shift x by x plus a. Clear? Some constant. So this is again invariant because it's a differential. So since you are moving with a constant distance, differential of that is 0. Clear? So it's invariant. We call this as a, if you are having Lorentz invariance plus translational invariance, we call that as a Poincare invariance. So Poincare is a larger group than the Lorentz group. So we say this S should be Poincare invariant. So this is invariant, it means this quantity should be invariant under Poincare transformation for the time being. There is one more invariance, what we call as gauge invariance. We will not talk about that in this lecture. We will talk it later on. For the time being, it should be actually invariant under what? Poincare transformations. Or if you simply say, it should be invariant under Lorentz transformation. Clear? So this is the condition for action in our field theory. Okay? Okay. So now let's try to derive the equations of motion. Okay? So, let's do something. Okay. So let's have the equations of motion in terms of this phi. Any question or any problem? How to derive that? So in mechanics, just now, just before we have said, you make a variation of what? Q to delta Q. Clear? Q plus delta Q. Now here we'll make a variation of what? Phi. Okay, so let's make a variation of this phi. So you are having this phi of x. It goes to some, okay, phi of x plus delta phi. So this is the variation of phi. Clear? So it means you are having, let's say, if this is a field of phi of x, you make a variation to, so you are having this as a delta phi. Huh? So this much is a delta phi. Clear? So what will happen to this partial mu phi of x? So it will go as partial mu phi of x plus delta partial mu phi of x. So it will be also varied. Clear? समझ आया? So this you can write, this object is same as partial mu delta phi of x. Okay, so this will be actually the assignment for you people. Show that this object is same as this. Okay? So now what will happen to the action? Now let's take that action. So you are having now the variation of s. So what it will be? Now tell me, when I am making this kind of variation, what it will be? Okay, simply, if I am making delta s variation, what it will be? So it should be now varying L, clear? So it will be something, let me write it as delta of L, that is a function of phi. Okay, so let me write x, let what is the variation? Okay, so now you make a Euler rule. Okay, is that known as Euler rule? Euler's theorem. So partial L by partial phi delta phi plus. Now tell me then partial L by partial. Okay, this one partial mu phi and then variation of partial mu phi. It is x here, huh? So I will not use x. I mean often. So this will. Okay. Clear? Hmm? Okay. Any question? So now look here. So these delta phi's are independent quantities, and you are having actually delta of this thing. And we know this delta, this very object is what? So this is same as partial mu delta phi of x. And I want to free it from this partial mu. What to do? I need to do a integration by parts. Now one point here. Since L is a function, clear? And you are making a derivative with respect to function. So usually you do the derivation with respect to coordinate, clear? Or a variable, simple variable. But here it is a function. So these are known as functional derivatives. Okay, when you are changing a function with respect to, so it means, so I will give the definition of these functional derivatives in next lecture or probably today. So what it means? It means, so what you measure simply a change of a given function if with respect to another function, simply how a given function changes and figure out the function change in the total function there. Clear? Got it? Okay. So now let's take this very object. So I will write this thing like partial mu partial L divided by partial mu phi of x. Okay, delta phi of x. So let's take this object. Okay, so as a total derivative. So now let's apply it. So it will be partial mu partial L by partial mu phi of x. Okay, so by product rule simply delta phi plus partial L by partial mu phi of x. Okay, partial mu delta phi. Okay, so now what I need to calculate? This very object. Is it? So this object is there. So how I can write it? This total derivative minus this quantity. Okay. So or I can write this partial L by partial mu phi of x. If you are not understanding it, just tell me, just stop me. Okay. So that's equal to partial mu partial L partial mu phi of x delta phi of x, okay, minus partial mu phi of x. Okay. Clear? Clear? Now what is there? There is an integration as well. Summation? Okay. So you can call this as first. So now if I integrate it, so let's integrate it over volume. So you are having d4 of x. Okay. Then you are having this d4 of x here. Then you are having a d4 of x here. Clear? So I have secured I have just written there. Okay. So now look here. So this is an integration over volume. It's a 4 volume. d4 of x is a 4 volume. So now it's a total derivative. It's at 4 divergence if you see. So you can call this entire object as what? F. Okay. So let's call this as an F. So it will depend on index mu. Clear? So it's actually del dot F. Okay. So let me write it. So we are having Gauss theorem like this thing. So let me write Gauss theorem. So it is integration over volume. omega. Okay, so let me write d4 of x. So if you are having partial mu f mu, so that's equal to integration over surface. Okay, so f, anybody, f mu ds mu, where ds is the hypersurface element. Clear? Got it? So now let's look at this objective. So apply the Gauss theorem. So this is f. Okay. So what it is? Partial mu f mu. समझ आवा? F is some quantity. Forget about it. F is. Okay. So what it will be? So you apply now Gauss theorem here. So it will be simply d. Okay. So let me write it over some s. Okay. So it will be some ds mu, and then what it will be? Partial L by partial mu phi and delta phi over some volume d. Clear? Everybody followed it? What I have done? Everybody? Okay. Good. Minds. So this will be as such d4 of x partial mu partial L by partial mu phi. Okay, and delta phi. Okay, now look here. So this is a surface integral. So we have converted a volume integral to a surface integral. Okay. So S is a hypersurface. You can write here. So now if my surface extends to the boundary, okay. So that means this so this is a surface term. So you need to evaluate this on the surface. What does that mean? You have to evaluate it on the boundary. Let's say you are having a volume. What is the boundary of a volume? A surface that encloses the volume. Clear? So on the surface, therefore, it should vanish. Because we are saying, by definition, fields have to vanish on the boundary. Clear? So this is the only condition we are having. So this will go to 0 at boundary. It's a boundary term. So in other words, so this object is simply equal to negative of that. Clear? So let's call this as second. So you second it first. So therefore I am having this. Okay, so using second in first. So I am having delta S. So it is d4 of x partial L by partial phi delta phi minus partial mu partial L by partial mu phi, okay, delta phi. Okay, since this is equal to 0, delta S by definition now it is 0. Okay, least action principle. Okay, so 0, so it means, okay, so I will write this is equal to 0, which implies then partial this L partial phi minus partial mu partial L partial phi. This is equal to 0. So these are your Euler-Lagrange equations, okay, for the field phi. This phi can be any field. Okay, so now let's take examples. Everybody has written? So let's take a simplest of the example. So let's take this Lagrangian to be half of partial mu phi minus half of m square phi square minus, let's write plus v of phi. Let's write minus. Let's not write this v. Okay. So let's write only this way too. Okay, so you are having Lagrangian of this kind, and I want to calculate the equation of motion, clear, from this Lagrangian. And phi is a scalar quantity. It is a single it's a single. It's a real quantity. Let's assume this phi is a real quantity. Clear? So that means I am having only one field here. So this you can apply to many fields as well. So you can put, if you are having many fields, then it will be actually an equation of motion for each field. Okay, I will take examples of those. It's one by one. Okay, so now let's, what I need to calculate? Partial L by partial phi. So let's calculate partial L by partial phi, which is a term which depends on only phi. So look here, it's a derivative term, clear? So phi is in the derivative, so it's a derivative term, you will get nothing from here. So this is a term where you are having phi dependence. So it will be simply equal to minus m square phi. Clear? When you make a differentiation, so simple rule of differentiation. Okay, I will talk about, how it comes. Okay, so you can think this as a simple variable and make a differentiation, simple differentiation. Clear? Okay. Subtlety of these things will arise later on when we will do the Poisson bracket. Okay. So now let's calculate that partial L by partial mu phi. Clear? So since mu is a free variable here, okay, and this mu is a dummy variable, so I will change this dummy variable to some another variable. I will write like this thing: partial by partial mu phi. Okay, so since this is the only term which contributes, I will put as half of partial alpha phi, partial alpha phi, like this thing. Clear? समझ आओ? Okay. So how many times these are?
2 times.
So it is simply partial phi square. You can think. Okay? Isn't it? It is partial phi multiplied by partial phi. You can think it as a partial phi square. You can do the term by term. Huh? You can put differentiation of this thing, keeping this aside by product rule. But I will not do that, but I will simply assume this is a square term. Clear? So when you make it as a square, so it is something partial phi square. Clear? So square, this 2 will come down, 2 and 2 goes. Clear? And 1 partial phi will come out. Okay, so let's write that partial alpha phi. So let's take this one out. So what you have to do then? Partial by partial mu phi, then partial alpha phi. Clear? So what I have done? Okay, so what is this equal to? Anybody? Anybody? So it is partial alpha phi. What this is? So if mu is equal to alpha, then it's equal to 1. Clear?
Yes, sir.
So but there is a problem. So mu is a which index? No. Is it a contravariant or a covariant? Anybody?
Contravariant.
Huh?
Contravariant.
Contravariant. And this? Okay, shall I write delta alpha mu here, or shall I write eta alpha mu? And like this thing, eta alpha mu. What should I write? This will be the exercise for you. Huh? Good. So it is simply, look here, partial by partial. Okay, look here. It is partial by partial x mu phi. So what you are having? Partial by partial, it is up. So it's x alpha phi. Clear? So what this will be? It will be actually a covariant index, and this will be a contravariant index. Clear? So समझ आया?
Yes, sir.
Because this is in the denominator. Huh? Okay, so when it will move up, so no, it is a contravariant index here. Huh? So it's already a contravariant index. What this is a? This will be a covariant index. Huh? So what it will be? It will be eta alpha mu. So you need to check it. Huh? So it is
They
eta
are
alpha
both
mu. What it will be?
contravariant.
So it is simply, yes, it is eta alpha mu. So it is partial mu phi. Clear? समझ आओ?
Yes, sir.
So just check it. So the definitions of this eta and delta. Okay, so it's partial mu phi. So now let's write there. So what I am having there for partial mu. Let me write this very term. Then I am having this term, partial mu phi. Okay, then you are having minus and minus m square phi is equal to 0. So what you get? So this is a DLM version plus m square and phi, that's equal to 0. So you have got the Klein-Gordon equation. So now you have seen Klein-Gordon equation is a field equation. It's a classic equation, a classical field equation. Okay, because I have taken this Lagrangian, it's a classical field, real field. Okay, and it is just governed by a Klein-Gordon equation. Now phi here, it is not a wave function. Phi is a field. Okay, so remember, it will be useful when we do the quantization of the real scalar field. Okay, so I will take from that very Lagrangian. Now if I do this way, so let's put this example. We have to do the same thing. Let's put a dagger here, and this half is removed. Let's put phi dagger phi. So how many fields are here? Phi is a now complex field, is it? So how many will be there? Two fields. So you are having two fields, phi and phi dagger. So these are independent. You apply the same equation. Okay, differentiation of phi with respect to phi. Okay, so you will get one Klein-Gordon equation. Then you do the differentiation with respect to phi dagger. You will get the another equation. Got my point? So you will be getting two equations. These equations, one for phi, another for phi dagger. Clear? So we call this as a complex scalar field. Lagrangian for the complex scalar field. And okay. One more point. Okay, so if this I have taken only the scalar field. If you are having a vector field, the electrodynamics, we have done a lot of electrodynamics. Okay, so it will be like this thing: partial in nu minus partial mu partial L by partial nu A nu is equal to 0. So let's say A is a vector field. It will be having an index. So now let take this Lagrangian. L is equal to minus 1 by 4 f mu nu minus j mu A mu. Okay, and you know what is f mu nu? Partial mu A nu minus partial mu A nu. Now calculate the equation of motion for this Lagrangian as well. Everybody followed it? So so you should be able to do these things. Okay, so let's stop here.